Let us discuss the moment generating function. It is one of the important function corresponding to a random variable x. So, we have learned that corresponding to a sample space or random phenomena, x is a random variable from x be a random variable, that means x is a measurable function from S to R, and to identify this we have different measure. One of the measure is that cumulative distribution function x, and if x is discrete, then we have learned probability mass function. If x is continuous, then it is probability density function. We can do some of the computations, like some of the measure moments and then mean variances. Now also we learn this transformation of random variables also. Now to another important function with for a random variable, it is known as moment generating function. So moment generating function, it is defined for a random variable x, is defined as mxt is expected value of tx. This is defined by summation of e to the power of tx px of xi in the case of discrete case, and it is minus m into plus m e to the power of tx fxx dx for a continuous case. Let us discuss this moment generating function. Let x be a random variable, the moment generating function, so we abbreviate like mgf, the moment generating function. So we abbreviate mgf or like this, or sometimes small mgf or mgf. So some of the, so these are or, so we abbreviate like that, of a random variable, the moment generating function of a random variable x is defined as mxt expected values of e to the power of tx. So now we know that if you take a function in general, we know suppose x is a random variable, it may be discrete or continuous. If x is discrete, then we know that it has some probability mass function. If it is a continuous, then it has some probability density function. So if you take a transformation y is equal to gx, we know that in a general how we can find the expected values of y. So expected values of gx, this is nothing but if it is a discrete, then all possible values xk, g of xk, probability the mass function xk. So whenever x is discrete, and if it is continuous, then this is fxx gx, this value taking gx fxx dx when if x is continuous. X is continuous. Now this is the general. Now here we are finding expected e to the power of tx. So here gx is e to the power of tx, for t is a real number. So if t is 0, then e to the power of 0 into x 1, it is gx will be nothing but 1. If t is 1, then e to the power of x. If t is 2, e to the power of 2x. If it is t is minus 3, e to the power of minus 3x. Then accordingly we have to find out expected value of tx. So now from this general formula we can, if you replace e to the power of tx, then this will be nothing but summation of xk e to the power of txk px of xk whenever x is discrete case, and then this is minus infinity to plus infinity e to the power of tx fxx dx if x is continuous. X is continuous. Okay. Now why this is called a moment generating function? Note that this moment generating function may or may not exist, because this sum has to be absolutely summable, then only these expected values exist. So this integration also has to be finitely exist. Otherwise, if it does not converge or it is infinitive, then we say moment generating. So it is called moment generating function if it exists for some values of t less than delta. So, delta is a real number, delta greater than 0. So, where delta is a real number, delta greater than 0. Basically, if it may or may not exist, but if it exists for a real number delta to delta, so suppose it is a this is a 0. So, delta is some number minus delta plus delta. If it exists for all t belongs to this interval, then we say that this moment generating function exists. Now, question is that if it exists, suppose we assume that for a random variable x, moment generating function exists. So, in that case, why it is called moment generating function? So, MGF moment generating function. So, moment generating function, why it is? So, it seems like it is generating some moments. So, assume that if the moment generating function exists, if the MGF exists, then finally, so then we define mxt is equal to expected value of e to the power of tx. Now, we know that e to the power of tx can be represented as a infinite sum. So, e to the power of tx can be represented as 1 plus tx plus t square x square by 2 factorial plus t cube x cube by 3 factorial, like this. So, t to the power r x to the power r by r factorial, like this. So, that can be represented. Now, this mxt, so mxt is, so expected values of e to the power of tx, which is expected values of 1 plus tx plus t square x square by 2 factorial plus t cube x cube by 3 factorial plus t to the power r x to the power r by r factorial, like this. It is just a general term. Now, using the properties of the expected value, it is nothing but expected values of 1 plus t into expected values of x plus t square by 2 factorial expected values of x square plus t cube by 3 factorial expected values of x cube plus t to the power r by r factorial expected values of x to the power r, like this. Now, expected value of 1 is 1 plus t into, you can recall that we have some notation. These are all the some raw moments. The rth order raw moments moment is defined as, so we denoted as mu r dash. This is nothing but expected values of x to the power r. So, then you can see that for r is equal to 0, mu 0 dash also we can write, it is expected of x to the power 0 is 1. So, this is nothing but 1. So, that we can write like this is mu 0 dash t into mu 1 dash plus t square by 2 factorial into mu 2 dash plus t cube by 3 factorial mu 3 dash, like this, t to the power r by r factorial mu r dash, like this. So, we can represent this moment generating function as a infinite sum of the moments and is with these coefficients. We can see that this expected values of tx can be represented in this way. So, 1 plus tx plus t square x square by 2 factorial. So, it is infinite series. Now, if we assume that this expected values of all the moments like rth order moment. So, rth order moment, the we know that the rth order, we say that raw moments of the random variable moments of x is defined as so we denoted mu r dash. So, you can recall that this is the notation we followed for r is equal to 1 2, like this. So, expected value x to the power 0, then mu 0 dash also you can define, this is nothing but 1. So, now we can say that mu 0 dash is equal to 1 and mu 1 dash is expected value of x. So, that in this way it is defined. Now, if we assume that all the moment exists, so then expected values of tx, now if you take the expected value both the side, so which implies expected values of e to the power of tx, this should be is equal to expected values of 1 plus tx plus t square x square by 2 factorial plus t cube xs cube by 3 factorial like this, plus t to the power of r x to the power r by r factorial this. So, after that let us write here. So, keep this, it is for recall that this is the notation we are following, and for the moments array order row moments. Now, from here we can get that, see that what is this? This is nothing but our definition mxt. If it exists for some particular values of t, like get less than some inner minus delta plus delta in a interval, then this can be represented as, now expected value, this property, using the expected value property, this is expected value of 1, then t is a constant expected value of x plus t square by 2 factorial expected values of x square like this, plus t cube by 3 factorial expected values of x cube, plus for particular general term to the power r factorial by r expected values of x to the power 4 plus like this. So, it is a infinite series. So, it is sum of a so now it can be represented in this way if it exists, all moments are exists. So, now all moment exists, then only we can represent in this way. Now, what is the right hand side? This is nothing but 1. So, 1 we can write like mu 0 plus like mu 0 dash, sorry, and then this is, so this dash is not a derivative, it is just a notation only, we discussed earlier also. So, plus t into this is mu 1 dash plus t square by 2 factorial into mu 2 dash plus t cube by 3 factorial into mu 3 dash plus t to the power of r by r factorial mu r dash, like this we can represent in this way. Now, why it is called moment generating function? Suppose this exists and some we know the, instead of the random variable, it is explicitly we do not know the distribution function or probability mass function in case of discrete, or probability density function in case of continuous random variable. Suppose we do not know, but we know the moment generating function. So, then using the moment generating function we can find the moments of this random variable. So, how we can do that? So, let us see that if you can differentiate with respect to t, so d dt of mxt, this is you can see that this is constant. So, this will be t into mu 1 dash is a constant, it will be with respect to t. So, it will be mu 1 dash plus 2t by 2 factorial mu 2 dash plus 3t square by 3 factorial mu 3 dash. So, like this, plus r into t to the power r minus 1 by r factorial mu r dash, so on. So, now if you differentiate second time, so just I want to let us write it again in the next page. So, mxt e to the power of tx, assuming that we can write it exists actually. So, this is mu naught dash plus t into mu 1 dash plus t square by 2 factorial into mu 2 dash plus t cube by 3 factorial into mu 3 dash, like this, t to the power r by r factorial into mu r dash. So, let us see that whatever later it is correct. So, now if you take the first derivative d dt of mxt, now this is a constant. Now, this is with respect to t mu 1 dash plus 2t into 2 factorial mu 2 dash, then 3t square by 3 factorial mu 3 dash 3t square plus like this, r t to the power r minus 1 by r factorial mu r dash. So, we can find this. So, now if you do the second time derivative d square by dt square mxt d2 by dt2. So, this is a constant again, and this 2 cancel, this is t. So, this is mu 2 dash plus, now this is 3 into 2 t square by 3 factorial mu 3 dash, like this, plus r into r minus 1 into t to the power r minus 2 by r factorial mu r dash, like this. So, now again if you differentiate this with respect to t, this function mxt, so this is become constant. Now, this is 3 into 2 6, this is also 3 factorial. So, then this cancel. So, then this is 1 minute. So 2 into this is t only 2t. So then if you differentiate with respect to t this, so this become a mu 3 dash plus there may be some term like now we can get some kind of similarity, some kind of trend we can understand now. So this will be like 432 into t by 4 factorial and mu 4 dash plus like this, and this is r into r minus 1 into r minus 2 into t to the power r minus 3 by r factorial mu r dash, so on. So in a we can now understand this strain that for a particular r, so if you differentiate mxt, so this will be starting from mu r dash and this become some r plus 1 factorial by r plus 1 factorial t into mu r plus 1 dash, so like this. So then this is the trend for r is equal to any 1 2 like this. So you can check that for r equal to 1 this is also true. So this is this is like some we can represent this. So now what we are gaining here from this expression, that now if you differentiate first time with respect to t and you evaluate at t is equal to 0, at t is equal to 0, what we will find? So it is nothing but mu 1 dash. So similarly if you second time you differentiate and then you evaluate this expression at put t is equal to 0, so then you will get mu 2 dash. So like this in general, if you rth order time you differentiate this moment generating function and whatever the expression you get, put t is equal to 0, then you will get the mu r dash. So rth order moment you can get. So here what we are gaining, that whenever suppose moment generating function is known to us, sometimes finding the moments using the probability mass function, probability density function may be complicated for some of the random variables. So in that case it may be simple in using moment generating function. Just we know the moment generating function, we differentiate r times and you then you put the expression at t is equal to 0, evaluate at t equal to 0, then we can get the rth order moment at from the moment generating function at t is equal to 0 if you differentiate rth order derivative, and if you evaluate at t is equal to 0, so then you will get the rth order raw moment. So that's why it is known as moment generating function. So now we will discuss some of the example how this moment generating function may be useful to finding those things. So let us consider this is one example. Let x be a Bernoulli random variable with parameter p belongs to 0 1. Find the moment generating function, mean and variance of x. So already we have computed those things, but here we will use this moment generating function. First we will find the moment generating function, what is the moment generating function for this case, and then we will find the mean and variance of x. Let us do that. Let x be a Bernoulli random variable with parameter p, belongs to 0 1. So it should be any closed interval, it can be 0 and 1 also. So then so here moment generating function not known to us, otherwise directly we could find from the moment generating function mean and variances. Here we first using the definition of moment generating function, we will find the moment generating function first. So the probability mass function of x is given by probability mass function px of xk, this is equal to p to the power of xk 1 minus p to the power of 1 minus xk, whenever xk value can take 0 and 1 and 0 otherwise. So the range of this random variable is 0 and 1 only. If it is 0, this probability is 1 minus p, it is 1, this probability is p. So the moment generating function mgf of x is given by moment generating function of x, mgf x is given by, so by definition this is mxt expected values of e to the power of tx. So because it is discrete, all the possible values of xk. So e to the power of t of xk, px of xk. So xk can take only 0 and 1. So if it is 0, so t into 0, px of 0 plus, so this sum you can see that just x equal to 0, then I put e to the power of t 0 into px 0 plus xk is equal to 1, then e to the power of t into 1 and px of 1. So then what we found, px 0, so this is e to the power of 0 1, px 0 is, so what is px 0, xk is 0, then 1 minus, so 1 minus p, so this is 1 minus p plus e to the power of t into px 1 is xk is equal to 1, this is p. So let us define 1 minus p is q for simplicity. So then p e to the power of t. So this is the movement genetic function of the random variable, a Bernoulli random variable x. So where q is equal to 1 minus p. So now you can see that this exists for any t, for a real number, any t, finite values of any value t, t belongs to real number, any real number it exists. So that's why this is, there is no problem. So now this mxt, using mxt we want to find the mean. So suppose first mean we want to find, so mu1 dash, this is expected values of x. So how we will find? We first differentiate with respect to, so first and mu2 dash also, because variance also we have to find, we want to find these two, then we using this formula of variance we can find the variance. So first we differentiate the homogeneity function with respect to t, mxt. So it is q plus p e to the power of t, so this will be p e to the power of t. Now second time we differentiate d square dt square mxt, this is also same p e to the power t. Even rth order derivative if you take, it will not be changing. So now from here you get that mu1 dash is expected value of x. This is if you differentiate this and then evaluate at t is equal to 0. So that is the our this is what we discussed here, that for any rth order moment you take the differentiation at r times and then evaluate t equal to 0. So now if you put t is equal to 0 here, this is nothing but is equal to p only. So similarly here also mu2 dash is d square, second time you are differentiating and then you evaluate at t is equal to 0. So then t is equal to 0, this is again p. So hence variance of x, because both mu1 and, so hence this mean of x, so mean is nothing but expected values of x. So mu1 dash, this we found p, and variance is variance of x, here we are finding, so variance of x. So expected values of x minus mu1 dash whole square. So we know the simplified formula is mu2 dash minus mu1 dash whole square. So mu2 dash also here equal to p, what we found. So that's why, so mu2 dash is p, so this is p minus mu1 dash also p square. So p into 1 minus p, so this is nothing but p into q. So in this random variable also you can check that for any rth order moment. So because if you do rth time derivative for any r, it does not change actually. So this is, you can see that this differentiation, it is p to the power t only it will be. So that's why this mxt, this is dtr. So this is nothing but p e to the power of t only. So which implies for any rth order mode, if here it can be easily found. So this is dtr mxt evaluate at t is equal to 0. So if you put t is equal to 0, this is p again. So this is one example that binomial for binomial random variable we can find this.